All right, everybody. I hope everyone had a good lunch. We'll get started in a minute. So if you settle down. Great. All right, welcome to our third session of the day. Our presenter is Professor Nilanajan Chakraborty from Stony, Brook University, and he's going to be presenting on machine learning fundamentals, right? Yes. Okay. All right. Okay. Let's welcome Nilanajan.
Thank you. So since we had a lot of theory from the morning, Anurag insisted that everybody be put to work. So I will, with the help of Srinath, we have something for everybody to get to work, and I will come to it in a minute. And that is the first thing we do. But before that, let me just say that thank you all for coming to this workshop, and it has been a wonderful couple of days up to now, and I am sure that the last couple of talks will also be wonderful. So we had a lot of more or less traditional topics in mechanism design and really cool applications of that. And what I will do today is introduce some of the background of some basic techniques in machine learning, which seems to be quite popular nowadays, but it has existed for a long time. And all the techniques that are popular now have also existed for a long time. So what I will do is the foundations, and then Anurag will talk a little bit more on the applications. And I will motivate it using one particular application from mechanism design, although there are many other possible applications. And
maybe I shouldn't.
No, it's okay. We will reduce the output a little bit.
okay, so let's start with some discussion from the end of the last talk. So Professor Agarwal asked a question that if I have some sort of a motion capture data from a human, how would you go about doing a type synthesis as well as dimensional synthesis for such mechanisms? So it's a very hard problem, and it is known as hard for a long time in mechanism design. So one of the questions there is that can machine learning help somehow? Okay, and so the picture that you see here is trying to take baby steps towards that direction. So what you see on the left are basically motion curves that have been input by the user, and what you see on the right are probable motion curves that a 4-bar mechanism or a 6-bar mechanism can generate. Okay, and what you see in the middle here is magic. And so this is the part of machine learning, and this is actually, no, this is drawn in this way. There's a reason for that. So this is a neural network. This part is known as a decoder, and this part is known as an encoder, and this part is known as a decoder. And the question is that what we'll try to do is understand what goes on in here from the basics so that we can get to this point. Okay? So I will not tell about the details of how to get to this point. I will end at this encoder decoder network, and Anurag will tell you a little bit more details, and then you will also talk about more traditional synthesis techniques. So as I promised, time to get to work. So what we have is a pre-trained network, and what you can do is play with this network and essentially draw these curves and see the output online in an interactive way. Okay, and it's a pre-trained network that Srinath has done, and he has produced a web interface for it. So if you click on this, those of you who want to do, if you click on this link here, once you get to the site, there will be some security issue, like JavaScript security thing, so you have to click once more to the link. So they will give some message maybe here, just click here and accept certificates or whatever, and you should get here. And as an example, I will try to draw a square.
We cannot see that.
Oh, because it's not duplicating my screen.
I think so.
Okay, so what is it? It's not duplicating my whole screen.
Probably the extended mode.
Yeah. Okay, good. Okay. So when I try to make this input this square, what this says is that the black dots here essentially gives some measure of probability that this curve can be possibly generated by a 4 or 6 bar mechanism. Okay? And I can draw different types of curves, and it will give me something. So I'll draw something which I don't think is possible to be generated. So you see in this portion, it's essentially saying, no, I'm not sure that I can do it. Okay. So has anybody tried and got it to work?
If you don't have a computer, you can also try it on your phone. Actually, it will work on the phone too.
Okay. Maybe I will stop for a minute or so so that.
Is that?
Doing this on mine, I don't know.
So there is a security issue, so you need to, it's just a JavaScript thing. You can also build it kind of incrementally if you want to and play with it.
Did you get it? know?
Anybody got it working? Traffic is too much? Okay.
The display settings on the top. No, the display settings on the top.
Okay, anybody had any luck?
It did work for some time, then it disappeared.
Okay, so you can play with it at your own leisure. So what I'm going to talk about right now is starting from the very fundamentals, how does one get to build this network, or what are the basis for building this network, okay? And so there is a ton of material available on the web about deep learning nowadays, and there are N+1 blogs if you want. So when I was preparing this talk, one of the things that I was kind of struggling with is that what will I give that is not there on these blogs? So that's a really hard question. So what I thought is that maybe what I can try to give is that since there is so much stuff, there is signal but also a lot of noise. So at least give you some basic understanding so that you can sift through the noise and get the signal out of all the things that are out there. Okay? So that is essentially the goal of my talk today. So let's start from the very basics. So learning, or typically what we mean by learning, can be classified into three basic types of questions or problems. The first is supervised learning. What it means is that you are given input-output pairs, or what is called label data set, and you want to compute a function that maps data to labels. Okay? So at its core, it is the question mathematically is that of function approximation. Okay? So fundamentally that's the question. And there are two types of problems which are called classification or regression problems. It depends upon whether your labels are integers or they are real variables. The next class of problems are called reinforcement learning problems, where you do not have explicit labels. So labels are assumed to be some sort of a correct value of the function at a particular point. Okay? It can be corrupted by a little bit of noise, but that's fine. For us right now, we can understand it as the correct value. However, reinforcement learning, in the reinforcement learning setting, you are not really given the correct value. What you are given is whether whatever you did currently was good or bad, some indication of that. What is the proper thing to do, that is never told. Okay? So that is the fundamental distinction between supervised learning and reinforcement learning. Another fundamental distinction is that reinforcement learning is usually used for sequential decision-making tasks. For example, a robot moving around in an environment and trying to decide where to go next. Whereas supervised learning is mainly done in kind of one-shot approach. Okay? And the next harder part, or in terms of learning, the harder problem is the unsupervised learning problem, where you don't have any labels or rewards. And your goal is to group data based on similarity. So for example, if you are shown 100 pictures of cats and 100 pictures of dogs, you are expected to kind of say that one is different from the other, but maybe not really give the label of cat or dog. So that's the difference. And you are never given any label when you are being given the examples. Another way of thinking about learning problems, which may be actually very useful for people in this community, especially because of interactive nature of design, is called active learning. In active learning, the difference between what I said before is that the input-output data is given. That means as a programmer, I just give it to you and the algorithm just acts on that. In active learning, the algorithm itself asks for the data. Okay? And it may ask for the data in a certain region of the input space. That would be the ideal way of doing active learning. And there is another concept of transfer learning which may also be useful, which is basically if you have learned one task, how is it useful in doing another task? For example, if you have learned, suppose magically you have learned how to design 4-bar mechanisms, synthesis from motion to, suppose you have done that. How does that inform designing 6-bar mechanisms? Okay. So that's the question there. So these are not very used, I mean transfer learning, some of it is used in this photo labeling tasks, but these are not used too much. So one of the things that I wanted to mention, which I forgot before, is that so we hear much about this, all these deep learning things, right? So Microsoft PowerPoint, if somebody has used recently, they have used a feature that in native PowerPoint on Windows, if you take in and paste, insert a picture, it will actually suggest you a label for the picture automatically. Okay? So when I was preparing the slides, Microsoft suggested me a couple of labels. So can somebody guess what may be a label of this picture on the top? It is hard to guess because the label was a picture containing text wall in node. And the label for the second one was a picture containing sky in node. Okay. So what am I trying to say here? I'm trying to point out a very important aspect of learning. That is, it is very dependent on the data set that you have learned on, your performance. It's true that the performance of learning in terms of vision is very impressive these days. But they are tested on particular data sets that they have curated over years. I don't believe ImageNet or CFAR10 or MNIST has anything like this. Okay? So it cannot do it on these data sets. And it brings to an important point which I will talk about later, is that is about distribution of the data. Anyways, that's interesting aspect in itself. So what I will focus today is basically on supervised learning, and so I will set up the problem formally, and there are a few components that are required to set up the problem formally. The first thing is that you have an input which is small x, which belongs to the space capital X, which is usually assumed to be a subspace of d-dimensional Euclidean space. So those who have listened to the talks this morning, Quaternions or SO3 and SC3 are not included in this. Okay, so you should realize that when you are trying to use many of these learning things in terms of rotation and transportations, you have to be a little bit careful, because most of the learning theory that is developed has an implicit assumption that this is a subset of RT. Okay, so you have to be careful about that. Although there has been some recent work where people do it on SC3, but most of the work is on RT. The second is the output level Y, which belongs to some set capital Y, and I will talk about what the difference capital Y's can be in the next slide. The third is that there is an unknown target function f. So this is an hypothesis that your data is generated by some unknown target function f. Okay? This has to be true for learning to work. If that is not true, then learning will not work. That it is not explicitly said, but that is an implicit hypothesis. And then you have your data, which I label here x1 to xn, and the capital N will always represent the number of data points. And the next thing you have is the hypothesis set. So I started by saying that supervised learning is a function approximation problem. And usually what people do in learning is to make the problem well posed. They basically assume some sort of functional form, make some assumption on what this possible class of functions can be, that is approximating the unknown function. That is called the hypothesis set. Okay? And this is the script H here. And usually I will try to stick to the basic convention that the boldface X is always vector, the boldface is vector, small is a scalar, and if you have matrix it is capital boldface. And D will always be my dimension of the data space. Okay? I'll try to maintain this convention throughout the talk. Okay. So what is the learning problem? Given this, so given the data set which is generated by this unknown target function f, compute a function g from the hypothesis set, and it is important to realize that g is always computed from a certain hypothesis set, such that g approximates f as closely as possible. Okay? And so there are lots of words in here. For example, approximates, what does it mean? Then what can be possible hypothesis sets? What can be possible output levels? So what I will do in the next few slides is basically go over each one of these questions one by one. Okay? Okay. So as I said at the beginning, depending on your value of your label, you have different classes of, different types of learning problems. So the first and arguably the most simple, let's say it's the most simple, is the binary classification problem, which has two labels, which is usually done as 0, 1 or minus 1, 1. Okay? So the set Y takes on these two values. Then there is a multi-class classification where the set Y is subset of the integers. So basically if you have 10 categories of objects, okay, then you can encode them as integers from 1 to 10 or 0 to 9. That's what it's done here. And the other is regression, where it's essentially the set of real numbers. Okay. So I started out by saying that the goal of learning is to find a function g that approximates f. So the first question that one should ask is it possible to approximate f? And in what sense is it possible to approximate f? And the second question is that, okay, then what does it mean for g to approximate f mathematically? In English we kind of understand intuitively. Mathematically, what is the definition that we use? So for the first question, so to understand why one should think about this question for a little bit, especially if you are kind of new to the subject, I think you should spend a little bit of time thinking about it. And you have seen this before, kind of, because everybody has done curve fitting, right? So that has some relationship to this. So think about a curve fitting problem where you are given 10 data points. How many curves can you fit through that? Through those 10 points? Infinitely many, right? I can give you 100 data points, infinitely many. So how do you even possibly hope to approximate with any one function? Right? So there is a kind of, if you just think about naively, there is a kind of problem or a blockage that you automatically arrive. Why do I talk about this? And that's the next point, is that if you think about it in a deterministic frame of mind, without any sort of other understanding of how the data is generated, then there is no way, you cannot do learning. Okay? So there is always implicit that there is some sort of knowledge about the way data is being generated. The usual assumption, and which you will see in every kind of learning book or paper, is that the data is generated from a probability distribution, which may be unknown, that's fine. But technically you need this assumption. Without that, the learning problem is not mathematically well posed. You cannot learn. Okay? And if this is true, then there are probabilistic guarantees possible on how well you can learn, and that's the whole field of statistical learning theory. Now I want to say another thing here, that you can possibly do without this assumption and make and do what is known as adversarial models of data generation, but then you have to model your adversary properly, like how bad can the data be generated. You have to model that. So that is something that people have looked at more recently, mostly in the context of online learning. But that's a little bit more sophisticated. This is the usual thing that is there in textbooks. Okay? Okay. So the main takeaway point from here is that the fact that people write that the data is generated IID, it is not just for any reason. Without that, the learning problem is not well defined. Okay? And IID I haven't put in here, but IID is required if you want to do any sort of mathematics usually. Okay? And I will talk about that a little bit. So now what I am going to focus on in the next few slides is basically on this question. What does it mean for a function g to approximate another function f? And this is a question in mathematics I think many of you may have seen before. And what people use in learning is a fairly straightforward notion of approximation, but I just want to go through it so that everybody is clear. So first what we need to define is a pointwise error. So remember, fx is my unknown function and gx is the function that I want to approximate f with. Okay? So at any point x in my domain, capital X, E of gx comma fx is basically the error or loss at that point. So I am calling it error function, people call it loss function. There are, both of these terms are used. Okay? So as an example, for classification problems, the error at any point is 1 if you do not agree on the given data point, and it is 0 if you agree. So this is just counting the number of times you have made a mistake. Okay? And for regression problems, the bottom one here is your square loss, which is kind of all around more or less familiar with it. So it is gx minus fx squared. You can also use the L1 loss or the absolute value loss, which is the absolute value of the difference between the two functions. Okay, so these are, so based on this, so this is where I think learning gets a little bit different from usual notion of when you think about approximating one function. So now we define two different notions of error based on those pointwise errors. One is called the in-sample error, the other is called the out-of-sample error. Okay? In-sample error means that you are averaging the loss over all your data points in your sample, and divided by n is basically the average. Okay? And since you know these data points, you can compute this. This is also known as the empirical loss. Okay? And if you will see, note one thing, is that many people, what they do is they introduce learning with the probability distribution on the data. I am avoiding it purposely just to make things a little bit clearer, but you should note that this, since you don't know the probability distribution, the only thing that you can do is calculate empirical loss, right? And this is empirical loss. Okay? So it is not in conflict with the probability assumption. It is still embedded in there. The data is generated. And the key is the bottom one, out of sample error. This is defined as something that measures how the function f is doing over the whole set x. Okay? And ideally what you want to do is minimize this E in G plus E out G. Okay? The sum of these two errors. If you minimize this, then you have learned your function pretty well over the entire domain capital X. Okay? And if this is small, then G is approximately F. So this is very straightforward kind of optimization logic. However, the only problem, as you might already realize, is that E out G is not really computable, because first of all, this set X may contain uncountably many number of points, and the second and the other thing is that you don't really know the whole set. You don't know, so this is not computable. This is called. So then why am I introducing it? It is important in terms of the concepts. Okay, so this is a term that you have heard quite a bit, and this is the generalization. So usually the first example that I showed you with the labels, if you talk to any machine learning expert, what they will say is that, okay, your trained network or your learned algorithm is not generalizing well. So what do they mean there? The formal definition of generalization error is the difference between the out of sample error and the in sample error. Okay? And why do we define it this way? Because we want to bound that. So we can say that the out of sample error is my in sample error plus my generalization error. Okay? And this is the way in which in machine learning you analyze an algorithm, or you think about an algorithm. So this formula is one of the most important formulas, at least to conceptually understand what learning does. So you have and how learning algorithms operate. You have two components of error. One is the in-sample error, the other is the generalization error. In-sample error you minimize by doing any sort of optimization routine, and that's what all the neural networks and everything is doing. The harder part is to handle this generalization error, to bound this generalization error, and that's a lot of people who work in statistical learning theory. What they are trying to do essentially is get a handle on this generalization error. Okay? And there is a lot of beautiful theory that actually does it, but unfortunately, as with most practical things, it's not enough. Okay? So the basic questions in any learning is that how can you ensure that the out of sample error is close to the in sample error? And the second is how can you make in sample error small enough? And both these problems are important. And what I want to emphasize is this is what makes learning different from optimization. Although optimization is routinely used, because in optimization you are just interested in this part. I mean, whatever your objective function is given to you, you just minimize that and you are happy. But in learning, that is not the goal, because your objective function is essentially a surrogate for the whole thing. Okay? So that's not the goal. And there is also a reason that I am emphasizing this, because historically, so why is there a certain resurgence in this neural networks and all these activities? Is it all hype, or there is some sort of technical substance to it also? So the way I understand it is that historically, and even 2 years back or 3 years back, the common wisdom was that you want to select your hypothesis set so that your generalization error is small, even though your in-sample error may be a little bit bigger. Okay? And to give you an example, again from curve fitting, if you are given 5 points, okay, so let's do much more simpler, 2 points. If you are given 2 points, you know a straight line will fit it, right? If you are given 3 points, you know a quadratic will fit it. So the question is that, should you use a quadratic always to fit 3 points? The answer usually is no, because your points may have errors, and then you are fitting the noise. So if you have d points and you use a polynomial of degree d minus 1, you can always fit it. But if you do that, you will be fitting noise. That is the usual wisdom. Okay? So you don't want to interpolate the points. Okay? However, modern neural networks try to actually exactly interpolate. They have much more, and basically what I'm saying is that they have much more number of data points, a much more number of parameters than the number of data points. Okay? So again, to the curve fitting example, suppose you have 10 points, you are surely not going to fit a 50-degree polynomial to it. If anybody says it, you will say you're crazy. Okay? But essentially they're doing something like that, because there are billions of parameters or millions of parameters, and there are maybe thousands, 100,000 data points, that's fine. But the number of parameters are millions. Okay? So that has essentially a kind of, and they are performing well practically in some cases. Okay? So that has essentially kind of made people rethink about this common wisdom. So I don't think the question is settled as of now, but I am pointing this out because many traditional machine learning books will tell that you should not overfit. And there is current evidence that says that you benefit by overfitting. So there's a confusion as to what is true. Okay? And I will show at the end one possible explanation that people have proposed recently. Okay? And it seems to make sense, and then they have showed it for linear systems and some more simpler systems, but I don't think it is a full solution for things like neural networks yet. Okay? So we'll get there. But I want you to keep this in mind. This is one of the points that is sticky. Okay. So now I will go back to the traditional way of thinking, which says, or this is essentially true. Effective learning is possible when this is small and this is small. Both of them are small. That is when effective learning is possible. Because that basically means E out G is small, and E in G is also small, so the sum will also be small. Okay? So that is the ideal case. If you can do that, you are very good. And the assumption of data being generated IID is required because that can actually help you bound this E out G minus E in G. Now, this is essentially a semester course by itself, so I cannot really do that. But I will give you kind of a flavor or an overview of what people usually ask in here, okay? And then I will talk mostly about this part.
But you don't know what is E out of G.
No, you don't know, but you can still bound, and that's where this assumption is required. Okay. You don't know. So that's the beauty of that theory, that even though you don't know, you can still bound, and it is probabilistic bound, and that's the next statement here. So this is the kind of guarantee. These are the kind of statements that you have. You cannot have any deterministic statement. What you can have is, for any given tolerance delta, which is greater than 0, with probability greater than 1 minus delta, this thing will be bounded by some function. This function has 3 quantities. One is that delta, which will naturally be there. One is this number of data points n, and the other is this quantity script m, and the whole fight is about how to pin down this script m, which is known as the complexity of the model class or hypothesis A. In the context of neural networks, it is also called the capacity of the neural network. Okay? People have terms for it, but it is not clear how to define it properly. Okay? Okay, so what I should say is that there are certain class of functions, for example linear functions, where people have actually derived exact formulas for these things and they are quite good. And for linear functions this term will basically become d plus 1, where d is the dimension of your data set x. Okay? So that is also called the VC dimension of your set. So there is a lot of theory for that, but all of the proofs, I mean, everything boils down to kind of thinking about in this term. Okay? So this is the common kind of picture through you can understand all the results. And this also gives you answers about how much sample you will need. If you have this formula, it can also tell you for achieving a certain precision epsilon, how much sample do you need. And you should note here that usually you want to choose delta to be high, like 0.95 or something, so that you can say with, or very small, 0.05, so that you can say with high probability that you are essentially guaranteed that this will be there. And note the statement, it is with high probability. So it is possible, even though you have done the best job, the function that you have learned does not do well. The guarantee is with high probability, 0.95. So there is a 5% chance that it is not doing well. So that needs to be understood in all of these things. Okay, so this I think I have said before. Okay, so now I have kind of covered the question of what does it mean to approximate and can you approximate. So I want to talk a little bit more about function approximation and using hypothesis sets. So how do we represent hypothesis sets? Okay, or what are the classes of hypothesis sets that we consider? Why do I want to do that? Because I want to contrast. So neural network is a function approximator, but I want to make sure that people understand what kind of, in what way is it the function is represented there. Because it is not very clear apparently that the neural network is representing a function, because it cannot be usually written down as a formula in closed form, but it actually represents a function. Okay? So that's why I want to talk about how do you kind of represent functions. So even if you don't have any kind of, okay, so this is a very big topic by itself in functional analysis. What I'm trying to give is very broad overview kind of thing, okay, which I hope you can relate to. Okay? So one of the things that is possible is to represent a function by linear combination of basis functions, and an example that all of you know is polynomials, right? Basically, even if you don't know advanced things like Chebyshev polynomials and all these things, you know monomials, like 1x, x squared, and you know that you can fit a polynomial curve to a data point, right? That when you are doing that, you are essentially using a combination. So if you are selecting an n-degree polynomial, you are using this basis function, and what you are doing is you are approximating your function using a weighted sum of your basis function. And these weights are essentially your coefficients of your polynomials. Okay? So that is one way to think about it. The other class which is very strong, useful and popular in machine learning, and I am just mentioning it here, I will not really use it anywhere, is known as radial basis functions. So what this does is basically it is saying that you have your data points, right, and you have the values of your function at the data points. What it says is that somehow at any given point, the value of your function is basically some weighted combination of a decaying function of the value at the given points. Okay, so okay, I should have a figure, but if you think about 3 different points and you want something in the middle, all these things are doing are basically on top of each point they're putting in some bumps. Okay, and then you are saying that any point is a weighted combination of these bumps. the value of the in function. That's what this says, but I will not use it. So this is just for information. So let's just move on from that. But this is the one that I want to spend more time on. So the key point in these things is that your function is linear in the weights. And one point to realize in learning, which is different from whatever you're usually do in functions, is in functions you always think as x as the unknown and the coefficients as the known. But in learning, your weights are the unknown, okay, or the coefficients are the unknown, and this x's, the so-called variables, are all known. Okay, so that is important to realize. Neural network is a representation where your function is a nonlinear function of the weights. Okay, and what you are doing is you are representing the function gx by a composition of simple functions. I have put in an example of a two-layer network that I could write down. Okay, so this w1 times x. So x is a d-dimensional vector. So think about this as some d1 times d matrix. Okay, so you are kind of doing a linear combination and then a max operation. Whatever you are getting here, you are multiplying with w2, and then you are basically doing the tan h operation on that, and that's your output. So your neural network essentially models functions in this format, and it's a composition of functions. Okay? So that's the way neural networks are actually implementing functions. Once you realize that, you should, with a little bit of work, which I will not show here, you should realize that I can replace these max or this tan h by more or less any function in a neural network. So one layer of the neural network, I can even replace it by an optimization problem or an equation solver. That can still be done. There is one caveat to it, that there should be some differentiability property. But it is important to realize that, because that's something that is being used nowadays, and that has potentially a lot of power. That you should think about the layers as just implementing some function, just the input as an output. And that function here are all explicit functions, but it may be a system of implicit functions also, or even an optimization problem. Okay? So that's why I wanted to kind of spend a little bit of time on this, how you represent functions. So this is the power of neural network, this way of representing the functions, which is not there in the other ones. Okay, so here I have just listed some of these hypothesis sets, and the key thing that I want to highlight here, which are in blue, is that you will see how I have written these hypothesis sets. I have written these functions as the weight. So I have written the polynomials as the coefficients of the polynomials. Okay. So what I have written here, if I read it in English, set of all coefficients of the polynomial such that y equal to w0 is the constant term, the coefficient of 1, plus wj to the power of j. So it's n-degree polynomial. Okay, that's what I have written here. Similarly, the linear functions, I have written it in terms of the coefficients here. So set of all w, because I am representing the whole class of functions, not just a single function. Okay, so if I change the weight, the linear function changes. So this is something that, so when I first taught the machine learning class about 2 years ago, this was one of the sticky points with students. So I just wanted to make sure that people understand that when you're representing sets of functions, the coefficients are the important things, not the variables. Okay. Radial basis functions, then there's another class of functions which are important because they are the basis of neural networks, and you can understand many things simply if you understand these perceptrons. So if you look at the perceptron, what this is doing is I am taking this linear function and then I am composing with a sine function. So what is a sine function? It will give you +1 if the quantity computed here is positive, it will give it 0. If it is 0, and it will give it -1 if the quantity computed here is negative. Okay? So that's what it will do. Sometimes you do greater than equal to 0 as +1, so I just put it in there, but you can do it +1, 0, -1. In binary classification, when you do greater than equal to, so I just put it +1 and -1, but that's a minor technical point. Okay? And then neural networks, and if you see here that I haven't written anything for the hypothesis set, it is not a mistake, because I cannot write it. Okay? It cannot be written essentially. Okay. So I have talked about the hypothesis set, and I have talked about the learning problem. I want to spend a little bit of time on data, because this is also important. So, and this is mostly important also in modern context. So, we usually, or at least the traditional view of machine learning was that you have data, you pre-process the data first. Okay? Pre-processing means centering, removing the variance, scaling things to have some nice properties. So that you still have to do. And then what you need to do is kind of transform the data a little bit, which is known as features. Okay? And many machine learning books or papers, you will see that they talk about directly features, not really data. And there's a reason for that, because people sometimes think they are equivalent, but there is essentially a step there. So a mapping from the input space to another space with dimension greater than or less than d is called a feature. Okay? Feature map. Okay? And whatever you get out are called the features. So I should have titled this as feature maps. Okay? Now, this is also FYI, I will not be using this much, but I will show the power of using features in the next couple of slides. So there are many techniques for doing features, usually doing dimensional reduction, and that's usually useful when you have motion capture data, because you are kind of capturing something for a kinematic mechanism, but you don't have that constraint within the data. I mean, you have that constraint embedded within the data, but not explicitly. So you usually do a dimensional reduction to get a more compact representation of data. And there are various methods like PCA, local linear embedding, variational autoencoders, which is the neural network version of this dimensional reduction, and which is what the picture was at the beginning, okay, which we're using. And it is not always that you want to reduce the dimensionality. Sometimes you may also actually want to increase the dimensionality and then reduce it. So there are versions known as kernel PCA, but we will not go there. Okay. So now that I have given you the basic setup, what I will go through is a couple of very simple learning methods and learning algorithms. And the main reason to go through it is that if you want to understand anything about learning, these are the two things you have to start with. If you don't understand these two, you are not going to understand anything else. You may be able to use PyTorch and Keras and whatever, but that's a different thing. Okay? So the first thing is linear regression. There is also another beauty about the linear regression. It's that it has essentially a closed form solution. Okay. So again, just to repeat, the hypothesis set is the set of all these coefficients of the weight vectors such that you have these linear relationships, and D is the dimension of my data. Okay, and Xj here is essentially the component. So okay, one more notation, I guess. If it isn't clear, when I'm using the not bold notation with J, it basically means the component. When I'm using the bold notation with the subscript, it is basically an index on the vector. So all of these are different vectors. It's a little confusing, but hopefully, if you notice whether it is bold or not, it will be clear. And when I will be using the component of x1, I will be using double subscripts. Okay. So we are given this data or the training data. Okay. So what you want is so what do you want in the linear regression problem? You want values of this W0 and Wj such that each one of these data points satisfy this linear relationship. Okay? So that's your goal. Now if you think about this, there are n data points and there are d equations. So it's not really, there are n equations and there are d plus 1 unknowns. Wj, there are d values here and this one, d plus 1. So it's not really a square system. So you have to learn it in a least square sense. Okay? So this is just writing this term in kind of a vectorial notation where I define this matrix X transpose just by stacking all these things up. So this is just machinations to basically write it in a compact form of y equal to X transpose W. And I wrote this in the linear form instead of this affine form because I appended this one here. It all works out. It's kind of standard algebra. And then if you have this as your objective, if this is your squared loss, mean square loss is your objective, then we all know that it has basically a closed form solution of this form. Okay. So that in essence is linear regression. But okay, so one point that I want to maintain here and mention here, and that's also, I mean, experts certainly know it, but it's a problem with beginners, is that linear regression means linear in the weights. It doesn't have to be linear in the data. That's very important. So I'll give an example in the next step, where what I will be doing is that, so when you are fitting a polynomial, it's actually linear regression. Okay? So that one needs to understand, although it is x to the power of n. So this is what I'm kind of going through here, is that this is how it is a linear regression. So what you do is that what you will be doing is computing all these features like x, x squared, x cubed. So if you're fitting a 3-degree polynomial, you'll be computing z1 equal to x, or so zi equal to x, x squared, x cubed, this vector, okay? And you will be appending the 1. And then this is what you will be writing as your approximating function. And the only thing here, m, is basically the degree of your polynomial. So that's the only change that you need to do. And then you just go through the same procedure. Instead of the matrix X, you have to just use Z and you will get your results. Here I have assumed X is a scalar because I'm doing polynomials, right? So Xi belongs to R. Okay? So I will not be going through it, but this same idea goes through in what is known as kernel regression. Okay? You can have complicated nonlinear transformations even of vector data based on the radial basis function kernels or some other functions, but as long as your weights are linear, these things all go through. That's the important part. Okay. So that was regression, and now I want to do the basic algorithm of classification using perceptrons. Why do I want to do that? Because essentially the algorithms that neural networks use is not much more complicated than it. It is huge, but conceptually it is not much more complicated. Okay. So what is our hypothesis set now? So there is a reason whenever I do any learning algorithm, I always write down this hypothesis set, because you should always try to realize that in a neural network, when you are changing your architecture of the network, you are changing your hypothesis set. That's what you are doing. Okay? So it is again the set of weights such that y equal to sine of this linear combination. Okay? And let's take two examples, and I take these two examples because I want to show you the power of using features. So this first example here, plus are kind of class, let's say +1, and the red circles are -1. And what we want to do is find a classifier, or essentially a straight line here that separates these two. And I have designed this data set in such a way that it is linearly separable, for it to be simple. Now, this problem here is a little bit more complicated, because as you can see, I have all these plus signs and I have these circles. There is no linear function that actually separates these plus and circles. Okay? But my claim is that using a nonlinear transformation of the data, you can still use a perceptron or kind of a linear classifier to classify it, and we'll show that in a minute. And I have purposely chosen this, that it is done in this way. So this is kind of not a natural data set, I just made it up to make the point. Okay, so another way of looking at the perceptron, and so historically perceptron was the first thing that came in. Okay, so I'm not going through the whole history, but because this picture is always used. So how do I represent this function computation here in a more diagrammatic way, or in a more pictorial way? So this is a picture for that. So this is your inputs 1 to xt. So basically the coefficient here, I'm basically putting 1 as an input for that, and these on the edges are basically the weights. So you are multiplying the weights by these inputs, you are summing them up and out comes s, and then you are passing this s through an activation function, which is known as an activation function. In this case, h happens to be sine of s. Okay? And this is the usual way things are represented, not in the hypothesis set way that I did, but I think there is usefulness to understanding the hypothesis set. So the first thing, what is the learning problem here? The learning problem here is that you want to determine the weights W0, W1, W2 that minimizes the number of errors in the training set. So that minimizes the classification error. So you can easily see that if I draw a line like this, there will be error. If I draw a line like this, there will be error. There is one particular line through here maybe that will have 0 error. Okay? And I do want that line. And you should realize that sine is not really a nice function to work with. Okay? It's not really differentiable. So although it seems like a simple problem, in terms of optimization, it's not really that nice of a problem. However, there was a very simple algorithm which is known as the Perceptron learning algorithm that was proposed again a long time back, which actually solves this problem in certain cases. So let me just say what this algorithm is, then I will say where it solves it. Okay. So you start with a random guess for the weights W. Okay? Then from the training set D, you pick a misclassified example. So you check every example, its sign. So you can put it in the linear equation, whether it's positive or negative. You can check the sign. Right? So you pick one of the examples that are misclassified. If everything is properly classified, you have your classifier. Pick one of the ones that is misclassified. Then you update the weight vector as W plus Yj times Xj. Okay? That's all that you do. And you keep doing it until the stopping criteria is met. Now the question is, what is the stopping criteria? So in practice, it should be some bound on the number of iterations. So this simple algorithm is guaranteed to converge, and there's a proof that it will converge. If your data is linearly separable, it is guaranteed to converge. Okay? But the key point that I want you to notice here that you're working with one example at a time. Okay? You're not looking at all the examples. So the problem with proving that this is correct and the proof is non-trivial is that you may undo what you did in the previous steps. Okay? Because once you change this, whatever you had correct before may become wrong again. So there is not really any monotonicity property. So proving convergence is hard without monotonicity properties. Okay? But still it can be proven, the convergence can be proven. And the key thing that I want you to note is that you are picking one example at a time in order to update your weights. And that is also the feature of currently how neural networks are trained. You pick not one but a small few number of examples at a time. You don't look at the whole error function. You're looking just a part of the error function, and that works. Okay. So for the linear function, it is fine. So there is one artifact of the plot here which may make it look a bit weird because these axes are different. So this data set looks a little bit weird, which I realized only this morning, but anyways, I hope you see that they are the same. Okay. Visually it looks a little bit weird. Okay, the main point is this second one. So here I have made the features with the x1 square and x2 square. Okay. With x and y, this data was not linearly separable, but it was separable with a circle, right? But circle is basically linear in x1 square and x2 square. So if I make the features non-linear, then it becomes linearly separable. So I'm not changing the algorithm. What I'm changing is I'm doing an operation on the data. I'm making features out of it, which are non-linear. And then my problem becomes the linear perceptron classifier basically classifies it, and in the actual space, x1, x2 space, it is non-linear. Okay? So that is a very big power, and that's what neural networks use quite a bit. And that's the reason that people talk about features and not data. Most practical cases, you need to transform your data into features. What earlier people were doing was handcrafting these features mostly, but nowadays there are better ways of doing the features. They automatically learn the features. That's also one more thing where people are excited about the new techniques. Okay, so now I think we are ready to get into neural networks. So how much time do we have?
You have 35 minutes.
35 minutes. Okay, so then let me stop and see if there are any questions up to this point. Yeah.
Just wondering, how do these methods work for multi-objective cases? You always distribute yourself to y belongs to some capital, set capital Y of dimension 1, right? So if the objective is multi-objective.
Yeah. So it's a very good question. So usually you can try to do one of two things.
Nilanajan, can you repeat the question? Please?
Okay, so to repeat the question, that I had an assumption that y belongs to the script y, and the script y was subset of a one-dimensional space. What if it is not a subset of a one-dimensional space, but it is a subset of a multi-dimensional space? Okay, so you have multi-dimensional labels. So that is not same as multi-objective. It's a little bit different, but I get your question. So there are two things that you can, there are a few things that you can do. One thing is that you learn separately for each one of them. That doesn't capture correlation in the output set, but it works if you do it individually. That's usually the thing people do. The second thing that you can do is try to capture the correlation and basically get an output that is kind of a single dimensional output that kind of captures it. That's another way people try. But usually, mostly it is that you load individually. Okay. Any other questions? Okay. So what I will do now is, okay, so the picture that I had of perceptron is essentially what a neural network is also doing. So this is one neuron in a neural network. What it is doing is, it is taking in, so this is the input to the neuron. It is doing a weighted sum of these components, and then it is passing through an activation function. Okay? And perceptron was the sign activation function, which we saw was that did not have good properties. So that is not usually what is used. People use smoother functions. Okay? So one way to smooth a sign is using a tan hyperbolic function. And that was one of the things that people used quite a bit earlier. But that also has its problems. So we'll see. Okay. So choices of activation functions. As I indicated before, it's a composition, right? So you can choose anything that you want as activation. But there are a few popular choices that people have used over the years. Sine you already talked about, then there is tan hyperbolic, logistic. This is the one that has come more with the current revolution of deep networks, rectified linear units, which is essentially max of x comma 0, I'll show you. And then there is this other operators that you can also use like max or soft max. Some of these are actually used in the final layer, and I'll talk about it a little bit. So tan hyperbolic is this function. So what is the importance of this function? It maps everything between -1 and -1. Okay? So it's basically bounding the magnitude of the output. So that was considered to be good. Logistic, it basically maps everything to between 0 and 1. So when I have this x you should think about in this slide as, I maybe should have used s, but it is this s here. Okay? Rectified linear unit, it is max of x comma 0. So if something is negative, you just reject it and put 0. If something is positive, you just pass it through. Okay? And I'll come to y. So this one has basically a vector input. All of these things are scalar input. This is a vector input, and what you are doing is just getting the maximum out of all the components of the vector. The softmax has a vector input and a vector output. You are getting this x, and what you are doing is, so I'm missing this I is not in the right place. It should be the subscript of x. So that is a to the power of xi by this. So you are kind of changing all these inputs so that it forms a probability distribution. Okay. So when you are doing classifier and you want an output as basically a probability of something being a dog or a cat or a buffalo or whatever, then you will use this softmax output. It will convert everything as a probability distribution on your class, different classes. Okay? And if you just want one level and you are brave enough to commit, you should use max. And max is also used in convolution neural networks. So just to give an idea of how these functions look like and what are the importance of these things. Okay, so the tan hyperbolic function looks like this. So there are a couple of things that you need to note about it. It is differentiable, but the derivatives here are not that informative. Right? The derivatives here are pretty small. Logistic also is good, but it kind of does it between 0 and 1. So when you are doing max, what you are doing is basically you are removing this portion, you are just making this flat and you are making this linear here. So the derivative properties are essentially good. Okay? So that is something that people, I will say why that is important in a little bit, but just note that the derivative properties are a little bit different here. change these things. Okay, so I said earlier that the neural network is basically modeling a composition of functions, and I had that expression out there. So let's just understand in more detail like what is it actually doing. So the first thing that I want you to note is something about notation. So whenever you have these circles here, what it basically means that you have something coming in, there is summation and the activation, both of them are applied and something goes out. Okay? So all of this summation and activation, that whole operation is done in one of these circles. So let's look at this from the innermost block. Okay? So I'm doing W1 times X. X is now a vector, right? So what that is doing is basically it is, so that is representing for everything done in the entire layer. But what is being done is that component wise, each of the x's that are coming in here, a row is multiplying this x vector. Okay, so a row is this weights, it is multiplying the x vector, and essentially it is feeding in here. The second row is doing it for that. The third row of that weight matrix is doing it for the fourth one, and so on. So that's just a compact notation. Okay, and okay, sorry, I should have. Okay, anyways, that's fine. Yeah, and then I have that max comma 0. So that, as you know now, is a ReLU function, right? So these are all my ReLU units. I have a summation and there is a ReLU unit in here. So the output of these things are max of, so this is max of W1 x1 comma 0, or the first row of W1 x comma 0. The output here is max of the second row of W1 x comma 0, and so on. Okay? And then what I am doing is that I am multiplying it by W2. So this is the main, so that is a vector here. This W2 is a vector here, because my output is just one dimension. Okay? So I am multiplying everything that is coming out here by W2, and then I am passing to the tan each function, which is located here, and I am getting my output y, which is basically between -1 and 1. Okay? So that's how this. So each one of these within the parenthesis is actually one layer. That's what I meant that you're composing functions. Okay? So you can have one layer as solving a system of linear equations or nonlinear equations. And what changes? The coefficients of those system of equations changes by changing this W1. And that is doable as long as the solutions have some good properties in terms of derivatives of the coefficients. So there are some technical properties required. But as long as you maintain that, you can think of these things as more general, and that has lots of power if you can use it that way. Okay? Any questions on this? The key thing that I want you to get is this composition aspect. That is, I think, key for applications when you try to apply it. So how do we set up the learning problem now using neural networks? So the loss function is basically average over the, so as I said, the neural network is implementing some function g. The loss function is basically, so here I am using one particular loss function, which is the average squared error. There are other possible loss functions that one can use. Okay? I'm just using one particular example, which is easy to work with. And as you saw before, this can be one example of gx, but it actually depends upon your architecture, number of layers, and if you change that, the class of function changes. Okay? Now, this is one thing that I want to say, which I did not say before. Usually, and that has to do something with the point of overfitting that I stated before. Usually you do not just minimize this in sample error. You add what is known as a regularizer term to it. Okay? And this minimization, first of all, is over the variables W. And W here is basically the set of all weights, which are the unknowns. And what does this regularizer term do? So regularizer is essentially a way to ensure that you don't overfit. And that's something that has been there in the previous literature. So as I gave you an example, right? If you have 10 data points, you don't want to fit a 50-degree polynomial because you have way more parameters. But if you think of 50-degree polynomial, but 48 of them are somehow linearly related, right? Then the number of degrees of freedom are just 2. Okay? So that may still be okay. So the regularizer essentially tries to do that. It puts a constraints on your weights so that your capacity of the model reduces. And all of this is hand waving. Okay. So these are okay. So for linear regression, there is a particular formalization of regularization. Okay. But when you come to neural networks and all these things are all guided by intuition and hand-wavy arguments. There is no preciseness in saying, okay, what amount of regularization do I need? It is not precise. But people say it works, so it works. Okay. So the goal now is to minimize this and essentially this function. So any questions about this? Yeah.
So if you, when we don't know how much to regularize, if you regularize too much, doesn't it become underfit?
Yes, it does. So you play with it. That's what you do. So one way of doing the regularization is basically either L1 or L2 norm of the weights. If you regularize too much, it underfits because essentially you are not minimizing this. There may be too much. But nowadays we are in the realm where they say that you should drag E in W to 0. So I'm not sure how much of that conventional wisdom still stands. But they still use regularizers. So that part is hand-wavy. Okay, so how do we optimize this function? So it's an unconstrained minimization problem, right? And it's kind of high school mathematics, set the gradient to 0. However, we don't know the function. Or we cannot write down the function in closed form, so you cannot set the gradient to 0. So a little bit more advanced mathematics, I guess, is that you do gradient descent. Okay. Why not Newton's method and all that stuff? Again, I mean, I'm not saying it is not doable. People have figured out ways nowadays to do this thing, but it is computation expensive. Again, the thing is that it is not, the function is not available in closed form, so it is expensive. So the first wave of neural network, actually, which was in the 1960s, that got stopped because there was no good way to compute the gradients. And the second wave, which started in the 1980s, started with the backpropagation algorithm, which is essentially an algorithm to compute the gradients efficiently over the neural network by doing two passes, which is known as the forward pass and backward pass. Now the backpropagation algorithm is complicated enough that it requires 45 minutes at least to explain. So I'm not going to attempt to do that. It is a clever application of chain rule, and everybody knows chain rule. And anyways, I mean, there is not much insight you will get from that unless you are really doing deep networks, and then you should understand how chain rule is working, because there will be problems with where the gradients are vanishing or exploding. That kind of problems can happen. So it is important to understand backpropagation properly. I'm not saying that it is not important, although there are multiple implementations available. But for us right now, we will not do that. What I will do instead is basically go more into stochastic gradient descent optimization, which is more of the current flavor of how things are done. Okay? And not tell how to exactly compute that gradient. That is something you can compute by that block. So as I said, the gradient has to be set to 0, and just to make sure everybody is on the same page, the gradient has to be with respect to the weight. And I changed capital W to small w, but hopefully that doesn't confuse you. Okay, so what we are searching for, so when we do gradient descent, what are you doing? We are searching for essentially, or let me not say gradient descent, let's say when you are doing any sort of optimization, what we are doing is we are trying to search, we are doing an iterative procedure where we are trying to search for a particular value of the weights such that our objective gets improved. Right? That's what you're doing. And you want to, so the formula that I've written here, it says Wt plus 1 equal to Wt plus eta t times Vt. And this vector is your direction of your search that you're computing, and eta t is, in learning theory they call it learning rate, in optimization they call it step length. It is the same thing. So your goal is to kind of compute this and this, and the optimization literature has a lot about how to compute this and what are the different ways to compute this. Gradient descent is just only one way, it's not the best way. There is conjugate gradient descent methods that are better if you're doing optimal control and all those kind of applications. Okay? And there are some other things called Nesterov acceleration methods. So essentially this Vt, one way of computing is just using the gradient at the current time step. It is just one way, it is not the only way. You can actually use the gradient at the current time step and some information from the past also. Those are known as, in general, momentum methods. They are also used in deep learning. Okay? So the idea is very simple. You have to get this Vt. You have two sources of information. What you have done in the past, what is your current gradient? And you need to somehow combine these two sources to say what will you do now. And since everything is local, you have to make sure that you are not going too far so that your locality is not becomes invalid. Okay? So that's the key idea. There are tens of different techniques, but it essentially boils down to understanding these two things. And okay, but why do people do tens of different things then? Because, and why is something better than the other? The hard part is proving that something is actually better than the other. That it will, so gradient descent has linear convergence. If you do something else, it will have quadratic convergence. It converges much faster. That is the hard part, the proof. Coming up with one algorithm is not really hard. You can just sit down now and come up with something. Okay. Okay. So now one part that I want you to understand here is that if we are trying to compute this gradient, right? So this E in W is a sum over n terms. N is my number of data points. And so this is basically over each example. N is my index over example, right? So for each example, how much error that I have. For each sample, how much error that I have. So if I have, let's say, 1,000,000 examples or 100,000 examples, you have those many terms. So that's very expensive to compute. I mean, in terms of principles, it is not hard, it is gradient and it's just dependent on one example. But computing all of them and getting the sum of them, that is computationally prohibitive if you have to do the arch numbers. Okay? So what you do instead is that you forget all about optimization and nice things, and then you say I will choose something randomly and do what is known as stochastic gradient descent. Now, what does that buy you and what do you lose from that? The good thing is that, okay, you cannot have deterministic guarantees anymore, but you still have guarantees that in expectation you will be converging to the local optimum. Okay, so that guarantee is there. What you buy is that this is very fast, but now what it doesn't happen is that there is no monotonicity in decrease of your error function. Your error may go up and down, that can happen. Okay? So what it means is that if your algorithm is not converging, you don't know whether you need to give it more time or you should actually stop. Okay? So that becomes hard to know. So I already talked about how to choose the, so this is what current versions of stochastic gradient descent does. So initialize at some bit W0 and you have eta 0. So in the optimization literature again, people have lots of literature on how to compute the optimal step length. But in terms of learning, you don't do that. You just usually keep a fixed, sometimes you vary it a little bit. But that's essentially heuristic, there is no principle to it. So while stopping criteria is not satisfied, and I have purposely left it as vague, like what is the stopping criteria, because there is no good one, you just use number of iterations. And you should also use the distance or the norm of the gradient. Those are also things that you use. So you draw kind of S indices. So I made it more general of drawing S indices from your data set, but actually what you do, and you will be implementing most of it with some software, is basically you kind of divide up your data set into bins and you basically get an index of the bin. Okay, so or batches, they call it batches, mini batches. Okay. So you compute this set of indices and then you compute the gradient over only those indices. Okay. And then you do your gradient update. That's all that you do. And you expect you just go out doing it, I mean, use some sort of web services or huge computing platform, you should be able to converge to somewhere. Okay, so so that's the basic idea now. So what are the key issues? And I talked about some of them, but let me just quickly go through it. So the optimization problem may be hard to solve, and this was especially true in the previous iterations of neural networks, and it often got stuck in local minima. Okay. Hard to use gradient descent because people usually didn't use gradient descent before. And there is another issue of what is known as vanishing gradients, which is if your weights go into a certain area, then if you increase the depth and if you do numerical computation, essentially, what you can find is that your changes in weights are not really affecting, or your change in the function is not really affecting your weights that much. And that is an issue that used to be an issue, and I'm sure that it is still an issue, but it is much less now. The performance, in early days what you had to do is basically you had to create the feature vectors. And For vision, there is a lot of thing about how to create feature vectors, but you had to essentially create this by hand most of the time. Okay? Even if you're doing PCA or something, you have to think how many components you will keep and all that stuff. And overfitting was a problem. There was good training performance, but poor test performance. Okay? All the regularization was used, but this was still an issue. Okay, so what does modern resurgence say about these problems? So for the first one, what do? They say it is hard to solve the optimization problem. What you should do is make the network larger. Increase the number of variables. And use stochastic gradient descent. Okay. Now, there is a lot of recent interesting work which is trying to understand why this is true from a mathematical point of view. So there is some kind of evidence, although for the full neural network nobody has shown that it actually makes a difference, but there is some evidence that when you increase the network size or when you are increasing the number of parameters, what you are doing is transforming the local minimas into saddle points, and you are creating many good local minimas. That's what, okay, that's how they describe it, but I'm not sure that all of that is mathematically well justified. But that's kind of the explanation. Okay? And so it becomes easier when you are doing a gradient descent. And when you are doing stochastic gradient descent, by the nature of the stochasticity, you are kind of avoiding local minimas. Okay. So with higher probability, you should land into good regions of the solution, even if it is not the global optimum. That is currently the justification. And there is some simpler networks where people try to show theoretically that that is true. But if you increase the parameters, it actually makes your optimization better. So the second thing, again, if you are, the first point here is hard to use gradient descent because, okay, if your number of data points get larger, how do you solve the problem? So let's say use stochastic gradients, and this issue of vanishing gradients, what they say is that instead of using this instead of using just single layer, you can do a cross connection. Okay. Feed input not just to the next one, but maybe 2 layers from now. That's the heuristic that people use. That supposedly works better. And so this is the point I think that has been addressed most strongly. So these things are more hand-wavy. There is some proof kind of in terms of practical results, but it is unclear that actually these problems have been taken care of now. But now, because you have multiple more powerful processors and there are many people working on it, so I guess many initial starting points, so you have better results. But the last point I think has been addressed more strongly. So this is essentially what the breakthrough in the vision part was, that you learn the features along with the function, and this is essentially the convolution neural network idea. Okay? So what I will do is kind of quickly go through the notion of convolution. What does convolution mean? With a very toy example, but I am hoping that it will make you understand, which you cannot understand by looking at pictures. Okay? So what is convolution doing? So the first of all, a picture is basically an array of numbers. Okay? So this is essentially representing a binary, a black and white picture. 1 being black, 0 being white, whatever you want. Okay? So what convolution neural network is trying to do is trying to come up with filters like this, which are kind of small blocks that you can pass along this whole picture, and whenever you get a hit of a particular pattern, a large number pops up. Okay, that's what it tries to do. So if you look at that 1, 1, 1 there's a pattern like that. Okay. So what is convolution? So let me just come up to, so right now I'll show the computation as to what is done in a convolution neural. What is the convolution computation that is done. Okay. So but remember, so I am showing these weights here as if they are known, but in the actual neural network, you are training to get these weights. These are not known, those are variables. Okay. Okay. So if you convolve this with this part, what does it mean? It means element-wise multiplication and addition. That's all that it means. Okay. So I do not believe that that's the formal definition of convolution, but that's how convolution is used here. Okay. So if you look at the first term, this 1, 1, 1, that basically gives rise to 3, and everything here is 0. So you multiply with the minus ones, you get 3. Okay. You add them up, you get 3. If you go to the next point, what you will get is that this one will give you a positive hit of 1. These two will give minus 2, so you will get a minus 1. Okay? And you just repeat this. If I did the arithmetic correctly, you just repeat this and you kind of get this row. Okay? So this is essentially the output of the layer. And I'm showing this in the matrix form, but you usually kind of flatten it out and do it in a vector form. Okay? And then you can just pass through it, and these are all the, so this whole 6 by 6 block now gets reduced to a 4 by 4 block because we're doing the convolutions. Instead of 36, you have 16 elements there. Okay? And again, the last one, you will see that there is this pattern, and so there is the hit. So the pattern has to be, these things has to be 0 and it has to be 1. If there is some 1 here, then that is not the pattern. So that's essentially convolution, and it is not that you just do one filter, you do a filter band. Okay. So in the AlexNet one that actually kind of created all this buzz, there were 128 such filters in the first layer. So you have to learn 128 such, and that I think the size was 5 by 5 or something, not 3 by 3, it was a little bigger. You have to create such big filters. Okay, this is just another example, I will not go through it. It's just here you are looking for the pattern 1, 1, 1 and then zeros, and actually is only here. So it will just give you hits of where the patterns are. And what you want to do after that is you want to do basically what is known as a pooling operation to see which one is the maximum one of this. So this 4 by 4 block, you may want to do 2 by 2 pooling to basically reduce it further to see which one is the maximum value. Okay? And that's what you want to pass through. So there are different interpretations of this, that you are getting edges and then different higher level features, and that is partially true. But you also get many nonsensical features. So some of them are sensible, some of them are not. At least to humans, it may be actually sensible. That's a different question.
So how do you choose those templates of?
You learn them. You don't choose them. So you have to only decide on the number of templates that you use and the size of the template. And there's a little bit more subtlety here that you may want to do some sort of zero padding here so that you ensure that you are even looking at the whole thing. But those are certain implementation details that are there. But you have to learn also. The main point is that you learn them, and those form the first few layers of your neural network. Okay? And then you have a couple of fully connected neural network like what people did in the 80s and 90s. And then yes, it's supposed to work. Okay. Since I'm running out of time, okay. So this is basically the AlexNet. Okay. Somehow I mangled it, put it upside down on something. But anyways, it should be read from this side. So you can see that it was many 7 hidden layers, and there were 3 layers or 4, 5 layers of basically convolution, and then 2 layers of this full architecture, and then just softmax because it was outputting a probability of the different classes of objects. Okay? So it's complex, but the concepts are essentially, you can break down the concepts and kind of understand it piece by piece. Yes.
So basically the convolution is doing, figuring out what are the best features to input to a neural network.
Yeah.
So the first few layers are basically figuring out what features to select and give it to.
Yeah, that's the interpretation. It is doing, so technically it is doing a mathematical operation, composition. Whether it is actually selecting the features or not, that's interpretation. Okay, anyways, so this was essentially the initial thing, the variational encoder. Anurag will talk more about it. I'll just say that what this is trying to do is that this has some convolution layers here, and what it is trying to do is getting the probability distribution of what generated the data and decode it to match the input and the output, but I don't think I have the time to talk about it. The only thing that I want to say is that the overfitting thing, the classical view is this, you will get it in all machine learning books, that if you make your model too complex, your out of sample error will increase, even though your in sample error decreases. That is overfitting. And the current view that is evolving is essentially something like this. And if you keep on training, make your model even more bigger, then you will reduce. That is supposed to be an explanation for why people, and there are current papers like 2018-19 that actually shows that for linear systems and some other simple systems. So I will put in some references for these things in the slides. Thank you, and questions.
So I have to say that there was a lot more insight in your presentation than you'll find anywhere on the internet, let me tell you. There are gazillion blogs and articles out there on this kind of stuff, and definitely you can read them and get started, but this was very insightful. So let's thank Professor Chakraborty. And if there are any questions, we can take that now.
Is slides available?
Yeah, I will put them.
Yes. He's going to make it available, so we'll put it.
I'll put them on. I'll add some references to some of these things and I'll put them on. I forgot to add the references.
So I understand that there is an amount of simplification and the assumption that all of the functions assumed are linear in the parameters. The functions assumed are linear in the parameters, the weights.
In what? In the neural networks?
Yeah. So the weights
No.
are it's not linear in the parameters.
No. So if you do tan H of W transpose X, that function is not linear in W, right?
So but then it's
So tan H is e to the power of what?
Right? Between two levels.
So there is a linear combination, then there is a non-linear function.
Yeah, I understand that.
Yes.
So is there like in some applications that is not possible even between two levels? So
It is not possible, meaning, so I'm trying to understand your
no, if
question.
I have another function, if I think it's more appropriate. For
You can
my-
use any function that you want.
No, but it's not linear between.
You have to just make sure that you can go through the derivatives with respect to the weights efficiently. Because linearity is not required.
It's not appropriate.
You have to just do the derivatives efficiently, that's all. So you have to understand back propagation properly. If you can do backdrop efficiently, it's fine.
Okay, all right, we'll take a break and be back at 3:30.
So simple. Just optimization. Just simple optimization. Whatever we are.
Part of it is just optimization.
We decide just choosing those functions are maybe somewhat
Currently, they have some theories about why these things work. They are really very exciting. So there are some papers which actually